namaste. Welcome to the next session of the module 5 where we are looking at GIS data quality. In my previous sessions, I spoke about what is an error, how an error can creep in your GIS data set, how you will actually try to address those errors. Then we also looked at data quality issues. We also spoke that your data should be complete. Okay, we also looked at logical consistency of your data. So all your and attribute issues with the attribute data, issues with the spatial data. So we looked at all of these aspects that are needed when you are addressing the data acquisition to the data model. Now in this part of the lecture, we'll extend the same discussion, but we'll also look at even the raster part of it. Okay, the raster model, what are the things that may come, and how do we look at the errors, how we look at the accuracy, and probably we'll also look at the pixel errors, which are extremely important in terms of understanding an image. Okay, so the concepts that I would speak about today is on raster to vector conversion. How do you convert a raster to a vector? So when you are converting a raster to a vector, what are the different errors that you may occur? It may come as an error. Then you will have mixed pixels issue. For example, in an let us take an pixel. So in case there are certain issues that is there in that particular data, or maybe its spatial resolution is very low. So you may see that a lot of different regions are clubbed together to form a single region. So that kind of issues may occur. So we'll address how we'll look at how do we address that issues also. Then methods of estimating error, what is the different kinds of error that may come using a mixed pixels, where we will look at two different methods, very well known methods. And then we will look at map accuracy assessment. So when I look at the accuracy assessment, I am looking at the raster data model, wherein we would look at both the confusion matrix and finally end it with the kappa. So kappa is one of the measurements of how we look at the classification system in a raster model. So these are the things that I would cover in today's lecture. So when I start, the first thing that I would like to speak about is the errors resulting in rasterizing a vector map, which means you are converting a vector map to a raster map. Okay, so grid, now when I say a vector map, it is in a point, line and a polygon. For example, I have taken a polygon here. Okay, this is a triangle that I have considered. So if I have considered this, this is the polygon that let us consider. So when we are, let's say we are converting it to a raster unit, which means we are converting it in a form of a pixel data. Okay, equal number of equal pixel size. Okay, that is how we will be doing. Now for example, when we are looking at this area of a triangle, identically should be about 7 units. Okay, so when we are converting it to into raster, for example, there I have shown here how it has been converted to raster. So you have this as 1 pixel unit. Okay, this has 1 pixel unit, this has 1 pixel unit, but when you look at this polygon, it is something like this. So you are actually approximating that particular polygon to that pixel, right? So when we are looking at any area, we may consider it as 6 or 7 units depending on how the cells and sides are counted in this particular triangle. But when you look at hypotenuse, you may have 7 cell sides long if 4 cells are considered as an approximate of the diagonal. Okay, if you consider this is a diagonal, if it is approximate of a diagonal, then you will consider it as a the 7 cell side long if it is 4 cells. Otherwise, if you consider it as 3 cells, then you may look it as at least 6 cell side. So this is what is the approximation error that you may get in a raster map. Okay, so if you consider very large grids, large size grids, only then your accuracy need to be understood in a bigger way. If it is, let's say you have the grid size extremely small, then such errors may not actually creep in if the grids are like this. okay. But if the grid is something like this, I will represent in a different color. If the grid is something like this, okay, so this representation may create a issue. So such errors also has to be handled when you are converting a vector data into a raster data. So this is one of those errors where which actually creeps in when you are trying to do analysis that has both vector and raster formats. So basically when you are converting this as a raster data. Now I will give you another example. For example, I have considered here, this is a map, this is a Hyderabad boundary. Okay. Now I have considered image that is exactly cut in terms of a Hyderabad boundary. Okay. Now this is a raster and this is a vector. What basically I have done is, I have taken this particular polygon, okay. Based on the polygon, I have approximated it and converted into a unit place into a vector. So now when you look at this particular region, for example, this is what I have here macroed in. So when you look at this, if you see possibly these regions, okay, when you look at these regions, these regions are those where the data is either missing or data is approximated, which means these many number of unit pixels are missing in that data, which means that you are actually removing that data that may be useful in certain terms. So this is also one kind of an error that may creep in when you are actually converting a vector data into a raster data. So then the second problem is mixed pixels. So each grid cell contains one single value. Whenever you have, for example, if you look at the Landsat data, each pix when you look at this is as a Landsat data, let us consider certain number of rows and columns. I have just taken 4 rows into 4 columns. Okay. In case if I am considering this, each is 30 meter by 30 meter. Okay. So if you look at your city region, okay, a city region, if there is a 30 meter by 30 meter pixel, it means this particular pixel can have various land uses here. This part may be urban, this may be for example water, okay, and this may be vegetation, and this may be in others category, right. So now what happens when you are actually this particular cell after imaging is being converted from analog signal into a digital signal where it is sampled, this entire region will be just converted as one signature. Okay. This particular signature actually belongs to a particular class, okay, or a digital number that belongs to a certain class. Now if this happens, this is called as a mixed pixel issue. Now because of number of classes that you have which are true representation of the real world, but when you look at your data model you have mixed pixel data. This is one of the big issues that we face when we have a data which is of a coarser resolution. Okay. So when I say coarser resolution, these are the data which when I refer to coarser, again coarser, when I say coarser resolution, it is reference to something. I am referring 30 meter data as coarser resolution with reference to 1 meter data or a 2 meter data that we have. So when I say 30 meter, each pixel will have 30 meter by 30 meter information. If I say if the spatial resolution is 1 meter, then each pixel will have 1 meter by 1 meter information, which means it is giving me more details. Okay. Let us say if this is your pixel, I am taking just one pixel out of here. Okay. So if we consider this as a pixel, now what happens if we consider this pixel, if it is let us say a 30 meter by 30 meter pixel, correct. So if there is let us say one building, there is one more building here, there is one more building here, there may be a small lake, okay, maybe a very small water body or a lake, or even a maybe a well, okay. Then there may be a playground. This is a, let us say, a playground. I will put this in maybe in different color. This is a playground, okay, and maybe this particular region is a water body. Other than this, these are buildings. Now, if this is a 30 meter pixel, 30 meter by 30 meter pixel, then entire region will be sampled as just one different class, okay. Whereas when you are looking at other regions, for example, let us say if the same thing, if I apply it to an 1 meter by 1 meter data, okay, this is a 30 meter by 30 meter data, the same pixel I have it here, but it is a 1 meter by 1 meter data from different satellite. Okay, let me consider it to be one of the triple satellite, which is 80 centimeter data, resampled it to 1 meter. Now I have 1 meter by 1 meter data. So this 1 meter data, for example, this particular building may be falling in maybe 3, 4, 5 pixels of this particular image. This may be another pixel, this may be another pixel, this may be another pixel. So when you are looking at this particular image, this is a building that you are capturing in both of this image, but in this it is just a part of a pixel, but here it is a larger part of many pixels. So what happens in this? This is actually a gross information, okay, or it gives you very less details about all of the quantities that are here, but this gives you a very detailed look about what quantities are there in this particular region, which means to say this has a better resolution, high resolution, and the one which you are referring here is a coarser resolution. This is a coarser resolution data, okay, whereas this is a high resolution data. So that is what we have to understand when we are trying to understand high resolution versus coarse resolution. Always when you are saying some data is high resolution, please refer to what reference you are saying. For me, the high resolution may be a 30 centimeter data or a 20 centimeter data. For someone who does not have an access to data, the 1 meter or 5 meter data may be a very high resolution that he or she can get. Some people 30 meter may be the very high resolution, but compared to what? Compared to 500 meter, 1 kilometer, 30 meter is a very high resolution that he or she may have access to, or 5 meter is very high resolution when compared to 100 meter or 500 meter data that he or she may have access to. So always look at the comparative statements when you are referring to any of the resolutions, or when you are referring to the pixel size, etc. Okay. So always be careful when you are mentioning it's a high resolution versus a coarse resolution, or high detail versus a low detail maps. Okay. So let us go back to what I was speaking about. So in medium resolution or coarse resolution, when compared to 1 meter data, maybe a 30 meter data, what I am considering here, a Landsat. So this particular pixel will have a number of different entities into it. So these entities will create a mixed pixel issue. So when have a mixed pixel issue, okay, let me give you one more example. This particular image that you are seeing here, this is an image from a triple sat data, okay, but this is an image from a Landsat data. Both are of the same region. This is probably from Bangalore. So this is a triple sat data. This is the Bangalore data that we can see. For example, when we go and look at this particular data, for example, you are looking at this data here. If you zoom in, you can see that the amount of details, for example, this is this particular thing is a lake, okay. This particular thing, whatever you are seeing here, is a water body or a lake, okay. So and this is the region which has a road. These are the buildings that you can see. So this is probably the Sankey tank, and this is the road that you see, and this is the Indian Institute of Science, Bangalore. So when you look at these buildings, you can very clearly get information about these buildings. So which means the detail is very high. So this is a high resolution map. Similarly, when I look at the same image here, if I look at the same image in the Landsat, okay, if you look at this particular region which I am pointing out, so the same image is shown in a very different way when you are trying to look at, if you cannot even identify what is the boundary of this particular water body. Okay, see, probably this is approximate boundary of this water body, whereas here you could have drawn the exact boundary with exact details of this water body, right. The one thing that I have done on both the images is nothing but called as a on screen digitizing. I have digitized that particular lake. You have to be extremely careful, it is not so direct as what I did, but you have to be extremely careful on those curves. So when you look at this, you cannot even find out where is the road, whereas the vegetation which you can find out here, and where this is the road that you normally find out. So very well known, the Sankey tank and the Sankey road. Okay, so that is what is the difference between a good resolution or a high resolution data and a coarse resolution data, or even Landsat is considered to be a medium resolution data. So when you why I try to explain this is that for you to understand why mixed pixel issue is extremely important, in order to address it, is that thing that you have to understand. So if the cell grid is extremely larger, then the features about which information is desired may not be extremely visible in terms when you have a low resolution or a coarse resolution data. When you have a high resolution data, this is extremely accessible. So how do we find out the errors that may have creeped in such vector to raster conversion? There are various different ways of calculating this error. The one of the very well known methods is Swister's method. So Swister's method is normally a very approximation method. So what it basically does is it Swister gave a general solution for estimating the precision of an image. He did not give any method for estimating accuracy, but he defined it as a precision of an image. It means his theory does not deal with any observational or locational error. The very important when you are trying to understand. This theory does not think about any of the observational or locational error. Okay, it assumes that error is solely based on points located at the centers of a grid cells to estimate the approximate grid version of the original map. Okay, what I mean to say here is, if this is a particular grid that has been converted from a raster to a vector, let us say this is the grid that I have. Okay, now I have converted a raster to a vector. Okay, green represents a raster to a vector. Now what it actually means is that it does not consider this particular information of position or the location where it is actually located in the entire grid, but it considers only the approximate the center values here, and looks at how good it is, whether it is displaced or it is in the estimated location, that is correct or not. Okay. So when you are looking at the Swister's method, it is more an approximate method than being an extremely viable method in terms of assessment of the error. So algorithm basically works on thematic maps, which are also called as chloropath maps, where when I say chloropath maps, these are special maps which have a shaded or a patterned regions using certain statistical techniques or statistical variable. Okay. So on which the homogeneous boundaries are separated by very infinitely thin boundaries. So that is what they mean by these are the homogeneously infinitely thin boundaries. So this is how the Swister's method works. It is more an approximation method and more looking at the central weight of a pixel in order to estimate what is the error that may have crept in. Okay. So there are several different methods that are being used, but Swister's is a very well known method. So he showed this by applying certain assumptions. Errors of mismatch can be corrected. Okay. this particular algorithm had huge number of assumptions. For example, first thing is this algorithm calculates for per polygon and then set of polygons what is the kind of error that may creep in. So, once it looks at the set of polygons, it tries to differentiate between what is a mismatch. So, once it finds out the mismatch between a pair of a polygon and a single polygon, then it says that this is the amount of error that has crept in. That is what is the algorithm of Swisser. Okay. So, when you are looking at this pixel pairs and pixel having that particular probability and looking at the frequency count, he just estimated. But what is a major thing is he missed out at the locational information that is necessary for any GIS data. Without tying it to the locational information, any method can fail in terms of providing the error details in a much larger context. If you have much bigger vector layers, then it is extremely difficult for us to find out the error. There is another method which was developed by Brett et al. So, this was based basically on a double conversion method. So, it is also very famously called as DCM method. Okay. So, the first vector to raster conversion here was made as it creates a base vector. So, here it does not just directly give you a vector to a raster data, but what basically this method does is it first gives you a base vector. Once you have the base vector, then the map is rasterized into very small grids and then compared. The base vector is then rasterized. So, whatever your base raster is first created, then you have a vector map that is converted into a raster map. Once you have a raster map, each of these raster map is then converted into small grids as small as possible and then compared with the base raster. So, now when we are comparing with the base raster, the cells in the base map differing from those in the finer map. That is, in the raster map, whatever is the cells that exist and are defining with the small gridded cells that you have converted from a vector to a raster, this provide an estimate of a error. The amount of error is then defined by the thin difference that may be there in the layer that is converted from vector to raster to a base raster map. Then this method basically looks at the locational error and also looks at the errors and the boundary index. That is why it is extremely efficient in terms of conversion from a vector to a raster. So, most importantly, it defines the boundary length in centimeter per centimeter square of that particular map. Okay. Then one thing that you can find out here is this rasterizing error is a linear function of the boundary index that it calculates. So, if you understand what is a linear function of the boundary index, how do you find the boundary index? So, if you calculate a linear function of this and try to substitute the values that are existing with each of the vector conversions, you will be able to find out how do you estimate an error between the thin lines of a base raster and a vector to raster converted data. Okay. So, this is this one method. So, most of your software that you may use in future course of time, any of the software, let us say ArcGIS, QGIS, etc., they have either one of these methods or more evolved methods that for example MCM, etc. So, these methods are then used in order to do a vector to raster conversion. So, you get more smoother polygons, smoother rasters than what you may have seen in these examples. So, most of the GIS software today, you do not understand what is the background of it, but these are the algorithms that actually drive those tools. These are the science behind those tools which are driving those software in order to convert a vector to a raster. So, there are certain errors with geocoding. For example, when you look at two major potential source that you can see in any of the images that are geocoded, it is error associated with a source map. First of all, a source map, if it does not have it has to be extremely precise. okay, extremely precise and accurate. If the accuracy and the precise and precision is much lesser, then obviously the error is there in the source map by itself. And errors also are associated with the digital representation, that these errors are quite easy to understand when you are looking at your own data set. So, apart from the correctable errors of the paper stretch or distortion, uh, errors also occurs with the boundary location or the boundaries that are not infinitely thin. For example, I gave you an example of how the vector is converted to a raster. Now, let us say I have a boundary line, okay, just to represent it as a form of a map. Now, I give a boundary line which may be 1.0 as thin or 10.0 as thin, depending on the way it has to be represented by me. Now, if I have 10.0 as thin, so it may cover that entire pixel which is actually converted into a raster map, okay, whereas 1.0 may even give some difference between the conversion that is already there. The pink lines would have been seen. So, that gives more of a different kind of representation. So, again this, if this is digitized and then converted, then it may also create a issue. For example, a 10.0 line may lie in between or to one of the sides. So, that again creates an digitizable errors. So, these are different errors that you can see when you are trying to geocode a line, geocode an image. Okay. For example, a line in 1:250,000 covers about 250 meters, but the same line in 1:100,000 covers 100 meter. Okay. So, for example, if you are drawing a line the same in a two different scale map, so 250 meter versus 100 meter, that is what is the difference that you may get in the boundary line conditions. And there is, as I explained, the digitizing curve errors. So, there are huge number of errors. For example, the one image that I have shown here, if this is a particular line, the exact line that I have, okay, then this we have seen more often. If I, let us say, I start digitizing this line, so what I do is I may, because of my digitizing, okay, sorry for this, if I look at the digitizing, I may just move out. So, which means that this is the error that we have created, and again here is the error and this is the error. So, these are the digitization errors that we would have done, for example here. So, these also can creep in when we are digitizing. So, errors can be everywhere. Only thing is that it is up to the user, it is up to the person who is actually creating the map to look at the standardized methods of looking at it, or look at it in a more detailed way in order to correct those different errors that may be in the entire data set. Okay. So, when we look at raster classification, when I say raster classification, I am actually looking at the land use classification. For example, when I look at this particular, on the left hand side, you find a satellite data. This is a Landsat data. Okay. This is representing a particular region. I think this is Coimbatore city. Okay. So, this particular classified map is we have created a land use map where you have classes as urban, vegetation, water and others. Red is representing urban, vegetation is represented by green, and water is represented by blue, others is represented by yellow. And we have used an algorithm that is called as Gaussian maximum likelihood classifier. So, now when we are when you detailedly look at this particular map, okay, for example, because of your classification, the input signatures that have been given, maybe you have given a huge number of heterogeneous signatures for this to be classified, this image to be classified as a land use map. Now, what has happened is that you can see there are certain errors that has already creeped in form of misclassification errors. You can see this red here around the water body, you can see this part here where you have a huge amount of red. I can zoom it in and show it to you probably. So, if we zoom it into this region, you can see this particular region of the water body is completely misclassified. Okay. So, this is a region that is misclassified, this is a region that is misclassified, and when you see this entire water body is misclassified. Okay. So, similarly we have another image here, this is a reference image. When you look at this particular entire region does not have a water at all. Okay. This particular region that is actually not an water body but an open space is classified as nothing but an water body. So, when you are looking at this particular water body, there has a certain amount of water, but here the urban was shown, but this particular region is not urban, but you have thick vegetated region. Okay. If you look at it, it is more of a vegetation. So, when you look at such issues, these are the issues which is actually make cause certain accuracy assessment measures to be put in place. So, there is something called as a map accuracy measurements. This is the task to compare a map that is prepared from a remote sense data and another map which is created from a different source material, basically used as a reference map, where it is accurately mapped onto the ground or onto the real world scenario. So, we assume, the basic assumption is that the reference map is accurate. That is a very basic assumption that we normally use, and both maps, when you are I am repeating it again and again, both maps, when you are actually comparing, both of them should be in the same reference system. Okay. When I say reference, same datum, same coordinate system, same projection. Okay. So, both maps must be of the same classification. If you have used 4 classes and the first class is urban, second is water, third is vegetation, and fourth is others, 4 classes of those categories, then the other maps also should be of the same 4 classes, if you have to compare about the accuracy, and both maps must be mapped at the same level of detail. So, if you are understanding this, then you will be able to understand what are the specifics that we will look at when you are looking at a particular map. So, everything should be same. Okay. Only thing is that the source, the way it is generated, is 2 different places. One is reference map is considered to be accurate, more accurate in terms of representing the real world phenomena, whereas the user created map is through algorithms that and is more of approximated map, wherein we train in the algorithm to automate the process of understanding every land use parcel in the entire region and classify every pixel into a particular class. Okay. That is what we mean by a classification map or a user map and a reference map. Now, so if this is understood, then the first way of looking at is using a confusion matrix, or very well known as a error matrix. Okay. In an evaluation of classification, a classification error matrix is a typically formed. It is a very well known method, and most of the classification systems use it as one of the authentic ways of looking at how best is your classified data. When I say classified data, it is dividing the earth surface into different user classes. When I say user classes, how humans have converted a particular parcel of land into his or her own use. It may be urban if you are looking at level 2 classification. If I am looking at level 3 classification, which means deeper classification, I may divide it into industries, buildings, residential buildings, etc. Now, if I have to really go into much deeper sections, I will divide it into residential building as HIG, MIG, LIG, etc. So, the amount of classification detail that you need depends on the user. So, it is not up to anyone to say this is what the classification detail has to be. What is the thing that you are trying to understand the phenomena, you try to look at that amount of classification detail. And one of the classification details that I would give an example here is the basic classification of level 2 class. So, now if I have created 4 classes, let us say urban, water, vegetation, others. Okay. So, you will have 2 images with the same reference details. Okay. Coordinate system is same, datum is same, and the projection details are same. One is a user map which you have created using your field data collection, and also with your one is a user map which you have collected in a field data collection and with signature collection and over the heterogeneous region, whereas other one is a reference map which is considered to be almost accurate. Now these are two maps. When we put it in the form of a diagonal elements, I will show you how it has to be done. For example, if we have two images, this is where you have a classified image, this is where the reference image lies. Now let us say you have two classes in this, class A and class B. Okay. So this is class A, this is class B. Now for class A, which was supposed to be class A in reference map, is also class A in classified map, that is a user map. So that is this many number of pixels. Class B, which was supposed to be class B in the reference map, is also class B in the user map, that is Z number of pixels. Okay. So the totally classified correct pixels is nothing but W plus Z. Okay. Now a particular pixel, okay, Y, is classified as for example, when you look at this particular image, this is, when we call this as, this is a producer accuracy and this is considered to be an user accuracy when you are computing this. Y pixel divided by total number of pixels. Okay. So this computes your producer's accuracy of a particular class. I will give you an example, so you will be able to understand it much better. For example, if I am considering this as an example here, for example, I have 4 classes that I have taken. I have 850 pixels which are supposed to be urban are classified as urban. I have 810 pixels which are supposed to be vegetation are classified as vegetation. I have 650 pixels which are supposed to be water are classified as water in my users map, but there are certain other pixels. For example, if other than any of these diagonal elements, all other pixels are those misclassified pixels. Now the first thing that I compute here is what is the producer's accuracy, that is what is the accuracy of your reference map with respect to the details that are there. So which means to say that now this is where you take your reference map. Okay. Reference map is always on the columns, whereas users map is always on the rows. So now when you want to look at the producer accuracy of urban, okay, you look at 850 pixels that are perfectly classified and you have total number of pixels is 901. So 850 by 901 is, this is your producer accuracy which is relative to your reference data. Now if I have to calculate how good is my classification accuracy, so you look at the same 850 pixels divided by the row total, that is 928. So this gives you the user's accuracy which is 91.58. Okay. So why do you need a producer accuracy and a user accuracy? Is to estimate how good is your user classified data versus the producer referred data. So a comparison of this will give you extremely important details in terms of how accurate is your information. Now if you want to calculate what is the overall accuracy of your image, considering both user accuracy and producer accuracy, you would be considering 850 plus 810, this is 850 plus 810 plus 650 plus 850 divided by total number of pixels. Okay. Total number of pixels is given here, it is including the error pixels that are there, total number of pixels in that particular image. So that gives you the overall accuracy of this. This means that your data has 90.64% of the data in your classified data with reference to a data that is considered is accurate. Okay. Without this kind of validation, it is difficult to provide any details to any governing agency or anyone saying that whatever the classification has been done. So this is one of the ways of looking at how accurate is your particular data. Okay. Now we looked at it. Another measure is looking at for example, another measure is to look at is using a kappa. So kappa or Cohen's kappa is a measurement of that compares the observed agreement is in agreement to expected by chance if the observer rating were independent. Okay. It is not quite dependent in term like your now overall accuracy. For example, when you look at kappa here, observed accuracy minus the chance agreement divided by 1 minus the chance agreement, the chance that particular that that pixel belongs to that particular class. So it goes pixel wise. The highest the value lies between 0 and 1. If it is 1, it is perfect agreement. If it is 0, it means to say that there is absolutely no agreement between the pixels. So let me take an example for this also, so that you will understand in a better way. Kappa is calculated by this particular formula that is represented here. Okay, this is a formula. Now if the same table is considered for this particular analysis, okay, so this is the total number of pixels. So the total number of pixels multiplied by the correctly classified pixels, that is 850, 810, 650 plus 680 minus, okay, then you have 928 cross 901, which means the row total 1 multiplied by the column total 1, okay, plus, that is for urban, then row total for vegetation multiplied by column total for vegetation, then row total for water multiplied by column total for water, then row total for others multiplied by column total. All of these are summed, okay, divided by the square of this total number of pixels that are there in that particular image minus again the same row total multiplied by the column total summed up. So this gives you the kappa value. For example, let us say whatever I have considered here have got a kappa value of 0.87. Now this value of 0.87 implies that the classification process was avoiding 87% of the errors that are completely random, completely random classification would generate. So you are avoiding 87% of errors. What many of the students do here is when they get 0.9 kappa, they say, sir, my accuracy is 0.9. It is not, your accuracy is not 0.9, but it means to say that you have actually avoided the 90% of errors that any random classification would generate. That's it. You are not actually very providing that this is accuracy of a data. Kappa gives you what is the avoidance rate in terms of when the misclassification would happen in other random classification measures. So that is what the kappa means. This is another way of looking at the raster data which is used for classification. So this is about kappa. These are different methods of looking at raster data. So now when we look at the summary, we looked at how to do what are the errors that may come from raster to vector classification. Errors that we looked at mixed pixels. I explained what is a large scale image and a small scale image and why the mixed pixel would come. So we looked at Swister's method and Brett et al. Method. I would recommend, in case I have not spoken here mathematically, but if you want to really understand both of these methods, you have to look at the background, the mathematical background behind it. It would be very easy for you to understand it in case you understand what do you mean by probability and the matrix operations. Then we looked at map accuracy assessment. We looked at two different methods, confusion matrix and coherence kappa. So all of these put together is terms where we are trying to look at the error part of the data, which is extremely important when your data is you are actually building up the data. Okay. So in the next class we will look at what are the different GIS tools that we have and how can we do the visualization part of it. So as of now, what I understand is that most of them who have taken this course would have understood how the GIS data is generated, what are different methods, okay, and what are the errors that may creep in. So now we are graduating towards building the GIS data. The first thing we have generated, we have looked at the generation of data, then we have looked at what are the different measures that we have to consider in order to have a good data. Now the next part we will look at is how do we store the data. Okay, maybe in the next lecture series I would look at what are the different databases, how it is stored. So that is how we graduate towards the end of the course where the software would be taught. So then we would in next class we will look at GIS tools and visualization as a part of just building up for the database analysis. So let's meet in the next class. Thank you very much. See you.